Okay, so this is a nice little paper that talks about something that may sound intuitively correct anyway. With warming, the atmosphere gets thirstier, which means it's going to start grabbing water from anywhere it can find, like from leaves when they open for photosynthesis, or from soils because latent heat loss is going to go up because the moisture gradient is going to get stronger, and so on. But this revisits that issue. This has been kind of discussed along the way anyway, but this does this in a much more systematic way, and they argue that they are more accurate in the way they are doing it, and so on. So let's just read and look at a few figures, and the discussion offers some hints as to why droughts are accelerating. So the title is Warming Accelerates Global Drought Severity. Drought is one of the most common and complex natural hazards affecting the environment, economies, and populations globally. However, there are significant uncertainties in global drought trends and a limited understanding of the extent to which a key driver, atmospheric evaporative demand (AED), impacts the recent evolution of the magnitude, frequency, duration, and areal extent of droughts. For all the extreme events, this is the idea: the intensity, duration, frequency, and scales. Right here, by developing an ensemble of high-resolution global drought datasets for 1901 to 2022, we find an increasing trend in drought severity worldwide. Our findings suggest AD has increased drought severity by an average of 40% globally. Not only are typically dry regions becoming drier, but also wet areas are experiencing drying trends. During the past 5 years, 2018 to 2012, the areas in drought have expanded by 74% on average compared with the 1981 to 2017 period, with AED contributing to 58% of this increase. The year 2022 was record-breaking, with 30% of the global land area affected by moderate and extreme droughts, 42% of which was attributed to increased AED. Our findings indicate that AED has an increasingly important role in driving severe droughts, and that this tendency will likely continue under future warming scenarios. Obviously something to worry about, but also we have to worry about the caveats, because a nice long drought data set from 1901 to 2022 offers a excellent resource for analyzing trends, decadal variabilities, and regime shifts, and so on. When you look at just a 5-year period, you always have to be careful, because it's just could be just a secular thing. On the other hand, this ends in 2022, but 2023-24 were record warm years. 2025, when I'm recording this in June, things are beginning to calm down, but in terms of the warming rates. But we have to see how this record warm years ended up adding to this drought severity story, right? So let's read some front material and then jump to drivers of change in drought before looking at some figures. Water availability has a critical role in shaping ecosystems, economic activities, and human livelihoods. Water is an essential resource for agriculture, energy, industry, and domestic use, influencing the overall sustainability and development of societies. Droughts are also detrimental for vegetation, reducing the carbon uptake of ecosystems, causing widespread plant mortality, and leading to significant disruptions in ecosystem functioning and biodiversity loss. They also negatively affect the productivity of annual and perennial crops, exacerbating food insecurity and economic instability. So lots of important points. With climate change, there is an expectation that droughts will be more frequent and intense, which already has been discussed, and the impacts on agricultural, environmental, and hydrological systems have increased as well. Observational evidence indicates an increase in hydrological and agricultural drought severity in several regions over recent decades, owing to the widespread increase in atmospheric evaporative demand, or AED, as well as regional declines in precipitation. Future projections from climate models also suggest a heightened severity of droughts in some regions owing to decreases in precipitation and enhanced AED. Okay, it's important to look at the historical records before jumping to projections, even though lots of papers only talk about the future without seeing whether the models that are projecting the future are also capturing the historic periods in terms of the duration, intensity, frequency, because there is already warming. If you haven't captured the response to warming already happening, then you have to be suspicious, or uncertainty could be high in the projections. Anyway, jumping ahead to I'm not going to go into the different types of droughts here, but there are meteorological, hydrological, agricultural, ecological droughts which depend on various depths of droughts, duration of droughts, and so on. Drivers of change in drought: to assess how changes in AED and precipitation affect drought, we compare SPAI trends calculated from observed AED and precipitation variations with those based on the climatological mean of AED, called AED climb in this paper. SPAI, of course, is the standardized precipitation and evapotranspiration index, which captures the drought. It's just one of the metrics. There are others as well. The Palmer Drought Severity Index is another one. People argue this is better than that and so on, but this paper uses this, so we'll stick with it. And precipitation here is PR climb, which is the climatological means at various locations. The quasi-global average 6-month SPEI trend based on observed precipitation and AED climb is 0.002 Z units per year, which is about 131% higher than the observed trend. Okay, so the 6-month SPEI trend. So we'll look at a figure to understand what we mean by that. I've jumped ahead quite a bit of the text, so let me clarify that. This indicates that holding AED to its climatological value results in a positive trend. In other words, when you compute these SPEI trends and use climatological atmospheric evaporative demand, then it tells you that the impact of AED, I'm stumbling a little bit, impact of AED is strong, right? So you can do these kind of sensitivity tests because SPEI has many variables going into it. You can hold them selectively to climatology and look at sensitivities of SPEI trends to the various variables that go into it. Okay, so holding AED to AED climb provides results in 131% higher than observed trend. So observed trend, of course, has AED varying throughout it, as we will see. When using observed AED and precipitation climatology, the SPI trend is minus 0.02 Z units per year, which is 300% more negative than the observed trend. So holding precipitation to climatology actually decreases the SPI trend line. Similarly, the trend in areas in drought based on observed precipitation and AED climb is minus 0.004% per year, which is 96% lower than observed trend. These findings indicate that AED changes from 1981 to 2022 intensified both the downwards trend in SPEI and the expansion of drought-affected areas. The time series based on precipitation climatology shows an evolution from positive SPEI values at the beginning of the study period to negative in recent years. This pattern is also observed with SPEI values based on ERA 5, which is atmospheric reanalysis product, highlighting the increased impact of AED as precipitation remains fixed at its climatological values. So these are basically how you would do sensitivities to separate the impact of precipitation changes versus atmospheric evaporative demand changes. Okay, one can be local global warming, advection of warm air, etc. impacts, Thirstier atmosphere impact versus the dynamic thermodynamic impact as seen in the local rainfall changes. Important to understand those differences, okay, or contributions. Monthly SPEI averaged, percentage of area in drought and maps of SPEI trends and the 2022 drought. So A and B here are showing quasi-global, so 50 south to 50 north average SPEI, HR SPEI, and global percentage area in droughts. So that's B. So you can see SPEI has got its variabilities coming up to 1951, and then suddenly I'm having a frog in my throat. So you can see the prominent drop here since the 1980 period, both in the HR SPEI trend in Z units per year and the HR SPEI trend. I'm trying to. So this is. Let's read the captions properly. I forgot what it is all about. When you read it, it's all clear. Then you wait for a few days to record it. I don't bother to read it again, but nonetheless, I will carry the points accurately. Don't worry about it. The trend in 6 months, so that is SPEI 06. Average HRSPEI for 1981 to 2022 in Z units, with non-significant trends marked in gray for visualization. So up to the grays here in the maps are not significant. So Western US obviously is a hot spot for droughts. It's climatologically a dry region. Parts of the Mediterranean, Eastern Europe, and of course Africa here, and parts of Central Eastern Eurasia, including large parts of China, and HRSPEI have increased over parts of India, both for August 2022 and the 6-month average running mean. Okay, 6-month running means for the 1981 to 2022 period. So here area in drought percentages have also gone up during this period. So as SPEI drops, the area covered by droughts go up as well. There are some details here on how they put together the ensemble means of various products. Precipitation is always tricky because it's very local, scales are small, the correlation scales are small, and multiple products exist, and they don't always agree on trends at any scale, even though similar or the same data may be going into producing these gridded time series, which are used in these global kind of calculations, because the way people fill the holes, fill the gaps in time and space, etc., are different, and those can end up resulting in differences in the product. So you always have to be careful, and this is something we just have to deal with, right? So these are trends in drought magnitude and frequency for 6-month SPEI during 1982 to 2022. This is the observed. So let's read what the different planals are. A and B, the trends in magnitude and frequency. So this is magnitude and frequency of droughts. So you can see here magnitude in Z units per year, and this is frequency in months per year. So frequencies have gone up in these brownish colors, except in some places where they seem to drop, but you can see there are large regions where there is no statistical significance. But if you hold AED to climatology, you can see how the contributions change. So this region becomes much smaller, this remains almost the same, this becomes smaller, this one even becomes more green or positive compared to the original observed. Similarly, when you hold climatology, AED to climatology for frequency, you get similar changes. So both duration, magnitude, and frequency are changed if you hold AED to climatology. That tells you the contribution to acceleration of drought intensities. Magnitude here, this is for 6 months. So this is the 6-month SPEI. I'm being a bit lazy here. Sorry about that. C and D, C and D are where we held AEDs to climatology. E and F obviously have to be difference in trend between observed precipitation and AED climatology. So you can see the differences. As we said, they light up in these few places, and it's a mix. So we'll read the drivers and then we'll understand these better, and they do the same thing for different regions of the globe, which basically give you a better sense of how things have changed if you look at the total observed magnitude and frequencies versus holding AED to climatology. This is the standard way of doing things when you want to see what are the dominant drivers of changes in magnitude and duration, frequency, intensity, and scales, right? Monthly time series and trend differences of 6-month SPEI during 1981 to 2022. Technically, you can argue that maybe this is multi-decadal variability and this will recover, but when you look at the longer time series, you know that they do the statistical tests as well. Nonetheless, if you had a very long time series, would there be some regimes where you will have multi-decadal time scales? It comes down to a matter of risk. When you have such a long time increase, multiple decades where drought severity is increasing, then you don't want to worry about whether it's natural variability or anthropogenic variability. You just want to understand what the drivers are and what to do about it in terms of managing the droughts, and you want to understand if this will continue into the future as well, right? So these are the quasi-global averages, so 50 south to 50 north. 6-month SPEI based on AED climatology. 6-month averaging gives you a sense of droughts that are persistent because if you look at higher frequencies, you may just get meteorological. So if rainfall is below average for a month, it may appear as a SPEI signal, but when you look at longer periods, you may want to look at more persistent ones, right? That's what they are doing with the 6-month SPEI climatology. So 6-month SPEI trends. Again, the lines here: AED climatology, precipitation climatology, and HR SPEI. So the total. I won't go into the detail, but there are different calculations here. Different data sets as well, to basically confirm that even when you use different data sets, you get consistent results, okay, in terms of the drivers as well as the trends. So this is the AED climatology map, and this is the precipitation climatology map. So this is the trend difference compared to observed. So this is just looking again at this in a different way. B is the trend difference between SPEI based on observations, so observed precipitation and AED, and SPEI based on observed precipitation and climatology of AED. So you allow precipitation to vary as observed, but you hold climatology of AED to climatology. And see the trend difference between SPEI based on observations and SPEI based on observed AED, but climatology of precipitation. Non-significant trends are in gray, and so on. So let's just look at one more figure. You get the idea of what they are doing. Let's just look at the drivers section to get a better sense. Percentage contribution of AED and precipitation trends in 6 months API, 6-month SPEI. So contributions can be pretty large in some places. So you can see that AED contribution is in the range of 40 to, let's say, 60 percent in the regions shown here, and in the Sahel as well as Central African region, large parts of regions here, contributions are zero. Again, consistent with what we have seen before. I have to watch out for my phone because I'm expecting a call. And precipitations contribute to much larger regions. Wherever you have blues here, tend to be yellowish colors here. That means AED is not contributing so much, but precipitation changes are contributing to SPI acceleration or drought intensity contributions. Okay, so you can see an anti-correlation here. Blues, yellows, blues, yellows, blues, yellows, and so on. So is there a clear signal in terms of tropics versus mid-latitudes versus other regions, let's say regions of droughts where signal to noise is very low anyway in terms of the precipitation signal? Well, you can look at different regions: Africa, Asia, Australia, Europe, and so on. So here it's easier to understand AED contribution and AED and precipitation contributions to SPEI, 6-month SPEI, are almost equal in Africa, but precipitation signal is slightly higher, whereas in Asia, precipitation contribution is much higher. Australia similar, Europe precipitation is much higher. So most places have much higher contribution from precipitation changes to SPEI, 6-month SPEI. Okay, so obviously there is a dynamic link. If you have colder temperatures, you expect that atmosphere will be getting warmer and thirstier, but not as strongly as the precipitation changes. Obviously here it could be snowfall changes, winter precipitation. We are not separating we are not calling them summer droughts, right? We are looking at SPEI throughout the year and doing 6-month averages. So just remember all those details. Okay. Overall, even though precipitation accounts for 60% of the global average SPEI trend during 1981 to 2022, the role of AED contributing 40% is substantial. This is especially notable considering the stronger sensitivity of SPEI to precipitation than to AED in most land regions. In Africa, Australia, and the drylands of North and South America, the influence of AED is particularly pronounced, contributing up to 65% drought trends during 1981 to 2022. Specifically, AED accounts for 44% of the drought trend in Africa and 51% in Australia, playing a significant role in intensifying drought severity in these regions. In contrast, the contribution of AED to drought trends in North and South America, Europe, and Asia is around 30%. Warmer, thirstier atmosphere is contributing much less over these regions, whereas AED is contributing much higher to SPEI trends over Africa and Australia. Okay, acceleration of droughts. Then the area affected by drought has expanded significantly, particularly during the last 5 years. So I will be careful about that because that's a very short period in terms of trends. Globally, during the past 5 years, 2018 to 2022, the observed area in drought was an average of 27%, which is 74% higher than during 1981 to 2017, and 58% higher compared with AED climatology. So precipitation and AED climatology is also playing a role here. Regionally, drought-affected areas increased by 119% in Australia, 163% in southern South America, 141% in the western US in 2018 to 2022 compared with 1981 to 2017. Similarly, in the past 5 years, drought areas increased by 75%, 80%, and 56% in East Africa, Northern Asia, and Europe, respectively. 5-year period socioeconomically for agriculture, for water resources, energy, etc., is still significant, but in terms of planning, we would have to know better whether that's really a trend that will continue or if it's a secular trend that will recover. Okay, so it's tricky to do that. Natural variability versus anthropogenic forcing. In contrast, when using AED climb, the increases were substantially lower in Australia, southern South America, western US, and northern Asia, whereas Europe and East Africa experienced a decrease of about 8%. A summary of these changes is provided in the extended data that you can look up. Okay. Drought severity in 2022 was record-breaking relative to the 1981 to 2022 period. The year 2022 had the highest drought area, 30%, which is 42% higher than in AED climb. So you have to always translate that. If you hold AED to climatology, then if the SPI goes up, that means precipitation is contributing more and so on. Because AED climb actually because precipitation is varying and AED is not varying, which means AED was contributing, so be careful. As shown in figure 1D, the 6-month SPEI for August 2022 indicates moderate to extreme droughts across Europe, East Africa, Western US and Southern South America, with drought-affected areas approximately 34 to 67% greater than AED climb. In addition, the average SPEI was minus 0.85 units per year compared with 0.52 units per year based on AED climb. Overall, owing to the observed increase in AED, the trends in SPEI and areas in drought during 1981 to 2022 indicate that not only are the drier regions becoming drier, but also wet areas are experiencing drying trends. So I will read a bit of the discussion. We have made all the main points, but if I fumbled it a little bit, maybe we can clarify them here. According to the SPEI, over the past 42 years, that is 1981 to 2022, global drought severity has intensified. In the past 5 to 10 years, this trend has accelerated as a consequence of the strong increase in AED. Okay, so that's very clear. Which is directly related to the global warming and increased vapor pressure deficit, as the water supply to the atmosphere is not enough to compensate for the large temperature increases. Some recent studies have also suggested an increase in the severity of drought events over large land areas based on metrics such as modeled soil moisture and the Palmer Drought Severity Index, all of which are sensitive to changes in AED. Nevertheless, in our study, we have quantified the contribution of AED to worsening drought conditions, which has been up to 60% in some regions, particularly in Africa, Australia, Western US, and Southern South America. Moreover, changes in AED have exacerbated the drying trend globally, particularly in the past decade. The year 2022 specifically was a record-breaking year for drought severity and extent in Europe and East Africa. So there was an extended La Nina, which would typically damp the warming trends because the ocean takes up more heat during the La Nina. But nonetheless, the warming has expressed itself as severe drought. And as I said, 2023-24 have to be considered after this because they were really record-breaking warm years. In Europe, the severity of the 2022 drought event can be largely attributed to anthropogenic warming, as the anomalies observed in stream flow, soil moisture, etc. cannot be explained by the precipitation deficit alone, but mostly by enhanced AED, which increased water losses by evaporation. So if AED is contributing a lot and we are mostly focusing on precipitation deficits for all our droughts, then obviously we have serious issues in terms of looking for droughts coming in the next few days, weeks, and figuring out how long they will persist, what their scale will be, and in the longer term, how their frequencies are changing as well, right? The year 2022, we already mentioned. In Europe, it was mostly anthropogenic contributions as inferred by attribution studies as well. So AED contributed a lot by increasing water losses via evaporation. Moreover, the ecological drought severity recorded in Europe's natural forests cannot be fully explained without considering the influence of high temperatures and AED on plant physiology. In the absence of formal attribution studies in other regions of the world that have experienced drought in 2022. The attribution in Europe and in the increase in severity globally driven by enhanced AED, as shown in the study, suggests that it's reasonable to conclude that the anthropogenic global warming likely contributed to the exacerbated global drought severity in 2022. Compared with previous studies analyzing recent drought trends based on atmospheric drought indices that use AED in calculations, this study has isolated the effect of AED on drought severity, and in addition, our study has also reduced uncertainties given the use of high spatial resolution and multi-source data. So they are basically trying to argue why the results are better than the already published results. The observed increase in drought severity aligns with associated impacts on agricultural, environmental, and hydrological systems as seen in events like the 2022 European drought. So you need multiple corroborations, and you get them via agricultural impacts and so on. Although SPEI is an atmospheric drought severity drought index that effectively captures the effects of precipitation and AED on drought severity, it may represent drought-related impacts very effectively. However, further studies are needed considering variables such as soil moisture, vegetation stress, hydrological flows, for better understanding of the broader impacts of the observed changes on ecosystems and human activities. Moreover, the observed acceleration of drought trends in the past few years aligns with future climate projections that indicate further increases in drought severity owing to projected warming, which warns of the need for better socioeconomic and environmental adaptation measures to reduce drought impacts and improve global drought. So you have to worry about extreme rain, flash droughts, etc. But now, obviously, you have to worry about the warming, the thirstier atmosphere, AED, and their impact on exacerbating drought durations, intensities, and frequencies and scales. Okay, so it's a good story, and this is already over 31 minutes, and I was a little bit not very clear in some parts, but the main message should be clear. Okay, see you in the next topic.